20-second delay, but that's fine. Like I'll let you know. Good, Nico, you can start.
Okay, I think we are live. So welcome everyone to the Latin American webinars on physics. Today we are super happy to have Hardi Veermäe from the National Institute of Chemical Physics and Biophysics in Tallinn, Estonia, where he's a researcher. And Hardi will talk today about probing primordial black holes with gravitational waves. So are you there, Hardi?
Yes.
So thanks a lot for accepting this invite. And please, the dance floor is all yours.
Yes, thanks, and thanks for the invitation. So, as said, I will be discussing primordial black holes, and primordial black holes have been a very active topic recently. So, in essence, primordial black holes are simply black holes that are formed in the early universe. There are several mechanisms: by inflation, by collapse of cosmic strings, in phase transitions. And today I will focus mainly on gravitational waves from primordial black hole mergers and gravitational waves that are induced by the formation mechanism that can also be used to probe primordial black hole scenarios. So let's have a look at the possibilities for primordial black hole abundance. So the mass range can be quite large. So the lowest masses are actually of the order of grams, but such black holes evaporate. So, okay, I cannot show. And black holes that do not evaporate, that can be actually components of dark matter, start from roughly 10 to the minus 16 solar masses. Before there are bounds from evaporation that will affect, for example, CMB or produce cosmic ray background. Then there are various constraints from microlensing that rule out relatively light primordial black hole candidates from, let's say, 10 to minus 11 up to 100 solar masses. So and around the LIGO mass range, which is roughly 1 to 100 solar masses, LIGO gives the strongest constraint right now, and this is what I will be discussing in the second part of the talk. And above that, you have constraints from accretion. So primordial black holes accrete, and the infalling gas will be hot and radiate, and it can affect, for example, the CMB. And there is a wide range of dynamical constraints, for example, white binaries. If you have primordial black holes in dark matter halos, then they can disrupt binaries, and just by the survival of white binaries, we can see we can infer that there are no primordial black holes in this range, and so there are several other such constraints. So, and this is a brief overview of what we can have. So, and let's look at the main applications or phenomenological scenarios. The window for primordial black holes as dark matter is open for relatively light black holes, as you can see on this plot. Then there is the option of primordial black holes as the seeds for supermassive black holes. So far it's unknown how supermassive black holes are formed. You need an intermediate black hole And one possibility of this is having an intermediate mass black hole as a primordial black hole that will then accrete and become supermassive black holes. And of course, the scenario that I will mostly discuss today is the primordial black hole scenario for the LIGO Virgo events. And yes, so let's move on. So the first thing that I will discuss is gravitational waves that are induced by primordial black hole formation. So if you have a large scalar perturbation, it will induce or it will source gravitational waves that can be picked up by the current or future gravitational wave experiments. So this is a rough, it's a plot for a power law spectrum. I would like to show, maybe I can do, no. So what you can see is that the scenario for light, primordial black hole dark matter is around 10 to minus, what was this, 10 to minus 16 solar masses, which is about 10 to 14 inverse megaparsecs. So, and the future experiments can test this scenario, while pulsar timing arrays can test scenarios that for heavier black holes that are about one solar mass or a bit heavier. And of course, so this gray line above is roughly the abundance that you need for the amplitude for the spectrum that you need to produce primordial black hole dark matter, all of it. So you need a peak that goes from the Planck, which we observe, to roughly 10 to minus 2 or 10 to minus 1. And as you can see, there are some observations like mu distortions of the CMB that can also constrain such peaks if they are not very narrow. If the slope is not very steep, because you have to pass the Kobe-Farkas bound. But okay, I need to hurry up. So recently, NANOGrav reported a potential signal for a gravitational wave background. So we should look at the first 5 bins. The last bins are probably just some random noise, and it's not clear that. So NANOGrav is a pulsar timing array, and they observed a residual noise in the timings of the pulsars, and they don't observe monopolar or dipolar correlations, which means that it cannot be easily explained by astrophysical sources or clock noises in clocks. But they also haven't found any quadrupolar correlations, which means that correlations between, or negative correlations between the pulsars with a 90-degree angle with respect to us, which would be a definite sign for a gravitational wave signal. So we cannot say that we have observed gravitational waves, but we can speculate. So what we did is we used 2 shapes for peaks in the primordial power spectrum. The first one is a broken power law, which shows up in most models of single field inflation that is used to produce primordial black holes. So it's a specific feature for when you have a quasi inflection point, and we choose the infrared tail to grow as k to the 4, and the UV tail should drop as k to the minus 0.5. In this way, we get end of inflation roughly at 50-60 EFOLs. And the second shape that we use is taken from a paper on hybrid inflation, which is log normal function with a slight modification that it has an exponential UV cutoff. And we also use specific parameters for the shape of the peak. So let's move on. So this is a plot of the induced gravitational waves over the amplitude of the peak in the power spectrum, A squared. So since the gravitational waves are induced at second order, then it's roughly quadratic in the, so it's roughly a square of the gravitational wave of the primordial power spectrum. So and I also show the blue line here is the induced gravitational wave signal for a delta function. So, but in general, you can see that the height of the signal is roughly the same. So maybe if you have a very narrow spectrum that's close to delta function, and this is difficult to make, you can get a small peak. But if we can make a very rough estimate showing that we don't have the NANOGrav signal doesn't predict enough power to have all dark matter in primordial black holes, which is what we need is roughly the amplitude has to be 0.02, which implies that the height is 2 × 10⁻⁸. But above, you can see that the NANOGrav signal, at least in the 1 sigma region, reaches up to 2.10⁻⁹. So it's 1 order of magnitude lower. But let's look at some of the details, because primordial black hole formation is exponentially sensitive to all the details in the formation. So what we use is we assume critical collapse, well, following this paper by Young et al. And the mass of the primordial black hole that is forming is roughly the size of the horizon when the fluctuations enter, times some factors. And if the density perturbation is below the threshold, you don't form anything. So what we assume, here I give the parameters, and we also use the nonlinear equation between the relation between the density contrast and the curvature fluctuations, which is important. It will suppress the abundance a lot. And so another technical detail is the mass function. So which we obtain by assuming Gaussian curvature perturbations. And as you can see, the primordial black holes, the sufficiently strong fluctuations that produce primordial black holes appear at the tail of the Gaussian distribution. So any modification to the Gaussian distribution can also affect the abundance a lot. And assuming the critical collapse, what we obtain a mass function that in the infrared is a power law, and in the ultraviolet, in the large mass range, is cut off exponentially. So this is a feature for critical collapse. And so these are the results. As I said, the LIGO Virgo scenario for primordial black holes is outside of the range. At least this is what we find. And but we can explain, for example, the primordial black hole scenario for the supermassive black hole seeds. Which is not in the middle of the range, but 2 sigma is good enough. And one more note that I want to make is that there are large theoretical uncertainties. For example, we used so our computation corresponds to the middle scenario. The middle choice, the yellow line for the critical collapse parameters, but as the formation depends, or the critical threshold depends, for example, on the shape of the overdensity, then it can vary by several orders of magnitude. However, we find that this variation is not enough, is not sufficiently large currently to bring the LIGO scenario into this into the NANOGrav range. But that I also have to mention that there are a few other papers that say that you could have solar mass primordial black holes, but this paper didn't consider the nonlinear relation between the density and the curvature fluctuations, which can suppress the abundance a lot. And if you change the cosmological background, for example, if the primordial black holes form in the matter-dominated period, then it's also possible to have heavy black holes consistent with the NANOGrav signal. And there was one more scenario that we didn't consider, is when you have a very flat power spectrum, then it's possible to have primordial black holes in the low mass window that's suitable for primordial black hole dark matter. So a brief summary of this part is that we can explain primordial supermassive black hole seeds with the NANOGrav signal, but it's not sufficiently large for the primordial for the LIGO Virgo primordial black hole scenario. And of course, if we have a positive measurement of a gravitational wave background, then we have to have a better understanding of the uncertainties related to primordial black hole formation, because this is the main. If you don't understand that, then it's difficult to make any definite conclusions. So, do you have any questions for this part?
Well, usually we have the questions at the very end, but I know you probably have some questions at this point. Well, I have one. You can hear me, right?
Yes.
So you mentioned, maybe I misunderstood, that black holes could have been produced during a matter-dominated era. So
yes,
there's an important phenomenological difference between black holes being produced in radiation or matter?
Well, the collapse of density perturbation is different in the two eras. In a radiation dominated epoch, all the fluctuations tend to be damped, but this is not the case in the matter dominated era. So it's easier to produce black holes, and you need smaller peaks.
Okay.
Okay, so if there are no more questions, then I will move to the second part of the talk. So primordial black hole mergers. And the formation of primordial black hole binaries. I can distinguish two different scenarios. So the first one is the early scenario where the primordial black holes form in the very early radiation-dominated universe, just by being close to each other and decoupling from expansion, so they start falling towards each other. And this is the mechanism that I will discuss today. And the second formation is so-called late formation, where the binaries form in dark matter halos by close encounters. And the rates for these two processes can be very different. However, since primordial black holes have a much small scale structure, so you form more small halos early on, then this can influence the late formation. So it can enhance late formation and it can disrupt early binaries. So these the two numbers will be probably a bit more closer to each other as on this slide. And the observed merger rate is about 10 cubic gigaparsec per year. And if we compare this to the early mechanism, then it's clear that if it's true, then it's difficult to have all black holes as dark matter because we would see too many mergers. But this is what we will discuss now in detail. So the rough idea of computing the number of mergers, the merger rate at any time, is that we have to take all the initial conditions in the early universe. So it's a random field of stationary black holes that will decouple and form pairs. So we just have to look at the initial density of primordial black hole pairs and look at how many of these pairs will form binaries that will merge today. So binaries that we can see with current experiments or see at all. Binaries that don't merge, we will not see. And of course, we also need to take into account that the binary that forms in the very early universe can be disrupted. It can interact with surrounding primordial black holes or surrounding matter and be perturbed. And we might not see it, or it might, it's very likely to merge at a different time. So this is the initial setup that we have. So in the early universe, it's just filled with primordial black holes that are at rest. And then at some point, they will decouple from the expansion. So they have an initial homing distance, and we also have to account for the closest black holes to the binary, because if you have a nearby black hole, it can fall into the binary and disrupt it, and we will not see the merger So we have to take this into account when we count the initial the pairs that will form binaries that merge today. We assume a boson distribution, so the black holes are distributed completely randomly. This is a good approximation, but it doesn't have to be true. We just there are ways to generate non-boson distributions, for example, by non-Gaussianity. And then to study the initial binary, we can just solve its evolution. So it will experience different forces, so expansion, which will become subdominant to the self-gravity term, so the attraction. And then there is a tidal force, a tidal torque from surrounding black holes, which prevents a head-on collision of these two black holes. So they will be very eccentric and they will start to orbit each other. So these are some details of the formation, which I don't want to discuss in too much detail. The essence is that we can compute the semi-major axis of the binary that's formed from the initial distance. We can compute the angular momentum from the torque, and we can do this statistically by summing the torques and averaging over the torques of all surrounding primordial black holes, and also matter perturbations. So all of this will contribute to the angular momentum. And since we have the initial separation and we have the angular momentum, we can compute the coalescence time of the black holes. And one thing that I want to turn your attention to is that it depends on the 7th power of the angular momentum, which is usually of the order of 10 to the minus 3. So in any collision with surrounding black holes, the angular momentum can decrease by, let's say, it becomes 10 to minus 1, and then the coalescence time can increase by 10 orders of magnitude. So it's really important that that initial eccentricity, which the binaries are very eccentric, they follow almost a line, is preserved. Otherwise, the initial binaries will not form or merge within the age of the universe. But once we know the distribution of distances of the semi-major axis, if we know the distribution of angular momenta, then we can compute the distribution of coalescence times, which means the merger rate. So, and we have performed the simulations. So this is an initial setup that we put a binary by hand that has the correct distance to form a binary that will go, merge within the age of the universe. We looked at the very early universe, so we had only 70 primordial 70 black holes up to 380 kiloyears of cosmic times, which means we roughly up to C and B, and we looked at simulations with the monochromatic mass distribution, where all the black holes have 30 solar masses, and the fraction of primordial black holes was 100, 10%, and 1%. And we run this each simulation 3,000 times and look at the survival of the binary, at the statistics of the angular momentum and the merger rate. And we also considered extended mass functions, where we had a number of 3, 10, and 30 solar mass black holes. And there is a typo here, so the fraction was 0.1%. Not the fraction was 10%, not 100%. And the expansion from dark matter, we look at the expanding universe, where the expansion, the dark matter component is accounted only by its contribution to expansion. We don't have any other dynamics for dark matter. So, and we test the statistics of the analytic predictions. So this is a simulation where if you can follow, then I think it was this primordial black hole, it will fall into the binary. So and the binary is immediately perturbed. So if you look at this again, if you didn't see, so you have this black dot above the 2 red dots, which is the central binary, which falls, and the binary is disrupted. And just as a second example of binaries, where the binary forms, it has the behavior as that we expect from our analytic estimates, but then it flies into a cluster and gets disrupted. So it slowly it picks up a satellite, and then it falls into this dense cluster and will be disrupted. And one more point that we want to make is that the redshift at this point is relatively high. But you can already see lots of small clusters of black holes. So the structure of the structure formation with primordial black hole starts immediately after matter radiation equality, and this can have a big impact on the survival of binaries, because these binaries will find themselves, or most of the binaries at least, will find themselves in these small clusters and be disrupted by interactions with other black holes. But this is not the case when you have only a fraction of dark matter in primordial black holes, because the noise introduced by black holes, primordial black holes, is small. And so we can distinguish 2 different types of disruption. The first is the disruption by the nearest neighbor. So when the closest black hole flies into the binary, and we can estimate the redshift when this happens by looking at when the closest binary is coupled to when the closest primordial black hole is coupled to the binary. And then we can estimate when it will form when it will fall into the binary, or the redshift when the closest approach happens, and from this we get the rough condition for the distance of the closest binary, the closest black hole to the binary. So it has to be farther than this y defined in this way. And The second source is disruption by clusters, which I will discuss later. So, but in the simulation, we can see that that this disruption rate is quite high, so we cannot neglect it. As for the implications for constraints or the theoretical predictions, when the fraction is small, then we can use, we can forget the disruption by clusters and compute only the fraction, the merger rate of initial binaries, assuming that they will not be disrupted later during the revolution. So a few results of the simulation is that the first plot shows the distribution of angular momenta, and we can see that the analytic estimate matches the numerical estimate very well. So the analytic estimate is the green curve, and the yellow curve is the angular momentum distribution of binaries that were disrupted but not ionized. So that a black hole fell into the binary, it could have formed a three-body system, and then one of the black holes flew out of the system. And this is the distribution that you roughly get. Yes. So the second point is that the initial binaries are very eccentric. So the angular momentum is roughly 10 to the minus 2, and the eccentricity is 1 minus j squared and the square root of it. Just to if you want to think in terms of eccentricities. And the final point is that initial binaries are hard, which means that the binding energy is much higher typically than the average kinetic energy of surrounding black holes, implying that if you have a binary black hole encounter, then this black hole cannot ionize the binary. So the binary can swap a black hole, but usually what you get is a new binary. So, and let's look at some of the plots again. So the second plot shows the change in lifetime. So we find that since we put in the central binary so that it should have the initial life merger time that coincides with the age of the universe, which is this tau 0, you find the peak around 1, which corresponds to the peak of unperturbed binaries. But we also see that when the binary is perturbed, so this yellow region, then the coalescence time is several orders of magnitude larger than the age of the universe, as I said before. So if you have this collection of binaries that you expect to merge and they meet with some other black holes, then you will never see them again. And the last panel shows that the binding energy, the ratio of the binding energies before and after a collision. And what we can see is that the binding energy, since the binaries are hard, and hard binaries, if they collide with other black holes, they tend to get harder. So the binding energy increases, the binaries become more compact, but the eccentricity decreases, angular momentum grows. So the collision times become much larger. So now, since we have the results, we can make predictions for the merger rate of binaries. And in this plot, we assume a log normal mass function. And we can see the effect of inclusion of different factors for suppression. So the blue line shows no suppression. The yellow line, so the yellow line accounts for the tidal torque from matter perturbations. The green line accounts for the suppression. So if we cut away the binaries that will interact with the closest primordial black hole, then this is the green line. And finally, if we account for the disruption in clusters, we get the black line. And it can be seen that its the effect is that the effect is to reduce the rate by several orders of magnitude when the fraction of primordial black holes is large. And finally, we can also estimate the merger rate of perturbed binaries. And it turns out that it can be dominant when the fraction of primordial black holes is large. But there are uncertainties in the computation. So if we move on, so the merger rate contains several factors. So the S in this formula is the suppression rate that can get contributions from several different sources, like the nearest neighbors or disruption in clusters. It also shows the dependence in time, which can be used to discriminate between the primordial black hole scenario for LIGO and the astrophysical scenario for LIGO, because as can be seen in the figure below, the merger rate is expected to go down for astrophysical mergers. So if we look at the high enough redshift, but for primordial black holes, it can go up. And another effect is the modification of the distribution of angular momenta or eccentricities by interactions with the surrounding matter that must be taken into account even if the fraction of primordial black holes is small. So, let me try now to estimate the suppression due to collisions of binaries and black holes in clusters. So we will assume several things. So first of all, it's a good assumption that when perturbed, when binary collides with a primordial black hole that is supposed to merge within the edge of the universe, then it will not, we will not see the merger. So we can just exclude this from the set of merging binaries. The second assumption is that we can assume we should estimate this minimal size of the clusters in which binaries can be perturbed. So since larger clusters form later, they are less dense and they are less likely to disrupt binaries. So we expect that there is a maximal cluster size above which binaries are unlikely to be disrupted. But we assume that that if within such a small cluster, the binary will be disrupted with certainty. And the last step would be to estimate the probability that the binary is inside of such a cluster. So if we know this probability, then we can estimate the fraction of binaries that will not contribute to the merger rate and which will effectively give the suppression rate for the mergers. And let's consider two timescales. The first timescale is the timescale of collisions. So we can take the cross section for a collision that changes the angular momentum by a significant amount. And since we know assuming that small clusters virialize fast, we know the velocity dispersion, we know the density, and we can estimate the time scale for collisions for a given cluster size. And we find out that the clusters that are smaller than that contain less than 2000 black holes, assuming that all of the dark matter is in primordial black holes, then such clusters will always disrupt the binary. So even relatively large clusters will disrupt the binaries. There is also an assumption for the mass here, which I don't remember. So of course the number will change if it changes the primordial black hole mass. And the second point is that if you have a larger cluster, then such clusters are not stable. So gravitating structures are not stable, and even if the collisions are infrequent, then as we know from the dynamics of globular clusters, the density inside the core of such clusters can start to increase. The binaries can also migrate toward the center of the cluster because binaries are heavier. They're bound systems and they are heavier than individual black holes. They can migrate into the core, and since the core density is increasing, then the black holes inside the core can become collisional, meaning that collisions in the core can have a time scale that is less than the age of the universe now. And if we take this into account, we get even an even larger number for the minimal size of the cluster that doesn't disrupt binaries. And taking the last number, we we count the black holes that are not within clusters of the size determined by the core collapse, and we can estimate the disruption or the suppression at the given redshift. And what we find is that for f equal 1, the suppression rate, the suppression of the merger rate is roughly consistent with our simulations. So even if the even if our strategy was designed to overestimate the suppression rate, we would assume that it should be not too far from the real suppression rate. And so to go back, then if we include this effect, we get this black line. So the final contribution is estimating the merger rate of perturbed binaries. Now, since if you assume that the initial binary, the initial pair, would form a binary that coalesces within the edge of the universe, then if it's perturbed, its coalescence time will be huge. So if we want to estimate the contribution of perturbed binaries formed in the early universe, we have to have a very compact distribution. A very compact setup of 3 black holes, and they will become bound before matter radiation equality. They will evolve, and eventually one of the black holes will be ejected from this 3-body system, and as a result we have a binary. The binary distribution of angular momenta is roughly independent of the initial distribution and has a power law distribution, which we estimate from our simulation and other work on 3-body collisions. So we get that this gamma, the power law, is roughly 1 or 2. So it's either the distribution is either constant, which is what we find, or it is linear in J, which is the equilibrium distribution of angular momenta. And I don't have time to go into details, which I didn't plan to do, but also accounting for the average energy of binding energy, or the average semi-major axis of this of binaries formed in this way, we can estimate the merger rate, and what we can see is that it has a different scaling with the fraction of primordial black holes. It has a different scaling with the mass, and it also has a different time dependence. That is, if this is a component that can dominate, then the distribution for primordial black hole scenarios can be very different from what we would expect if the initial non-perturbed binaries contribute to the merger rate. And the final point is that since these binaries don't have very high eccentricities, and in fact the eccentricity distribution is close to the equilibrium one, then further collisions in later halos will not increase the coalescence time. But since hard binaries tend to get harder, then the semi-major axis will decrease, which tends to increase the merger rate. So if you have lots of small-scale structure that will perturb the binaries later, then the merger rate can actually be higher than what we estimate here. But we didn't take this into account. So
better, Hardi, to start wrapping up.
Yes, so this is the one of the second to last slide. So if you fit the mass function, the log normal mass function to the events found by LIGO and Virgo collaboration, we can characterize the parameters of the distribution, and we find that the mass, the central mass, is roughly 20 solar masses, while the distribution is relatively narrow, so it's 0.5, which means roughly 1 order of magnitude on either side. The gray line accounts for the constraints on primordial black holes, and the points above the gray line are excluded by several constraints in the 1 to 100 mass region. And we also find the constraints from LIGO, since the scenario, the suppression rate is expected to be conservative. It's difficult to imagine how to suppress this or how to explain the constraint way further. But of course, there are several theoretical uncertainties associated to this process. So, but this is the result that we get. And in the plot, the black dashed line denotes the region where we can explain the LIGO events. But since we don't see many 100 solar mass black holes, then the constraint is obtained by requiring that we don't see any mergers. So we account for the actual mass distribution that we obtain by LIGO. We don't just fit the merger rate. And this is a work in progress. We also show the constraints or potential constraints from individual mergers on the left, and on the right we show the constraints from a stochastic gravitational background. This is something that I didn't discuss in the talk, but when the binaries merge and they are, let's say, too far to pick up the signal for the individual merger, then they will contribute to the gravitational wave background. And it's also possible to constrain primordial black holes using this background. And in fact, I don't have a slide for this, but using the stochastic gravitational wave background from binaries, since it depends on the redshift dependence, it's also possible to look at the background and distinguish the primordial black hole scenarios and astrophysical scenarios, because as I said, in astrophysical scenarios, the mergers at high redshifts are more infrequent. And I will summarize. So we find that the primordial black hole scenario for the LIGO Virgo events is possible roughly when the abundance is between 0.1 to 5%. And one important point is that so when the abundance is small, then we don't have to account for the disruption and all this nonlinear evolution in the late universe. But if the abundance is relatively large, so even for 5%, this can affect, for example, the time dependence or the gravitational wave backgrounds that allow. So that what I want to say is the signature for separating the primordial and the astrophysical scenarios might change a bit if you have a larger fraction, and this needs to be understood better. And of course, so after our paper, there has been more work. So accretion has been shown to change the predictions, and it can relax the constraints. There have been studies of the small scale structure formation, that is the clusters of black holes, where they show that also since there is small scale structure that is enhanced, you can have a larger late binary merger rate that can also contribute, that can be picked up, that can be large enough to be visible by LIGO and Virgo. And this will also change the characteristics of the primordial black hole scenario. And there have also been a few other studies. So this is it. Thank you for listening, and I will answer any questions if you have some.
Thank you very much, Hardi, for the talk. So I can see already a few questions in the YouTube chat. So guys, don't hesitate to send your question to Hardi via the YouTube chat, please, also via Twitter. So there's one from Ivanova. Ivanova is asking, do you need to assume a specific PBH population size to obtain the rate of mergers in both the early and late cases?
Sorry, this is in chat. I didn't understand.
Okay, the question is if you need to assume a specific PBH population size to obtain the rate of mergers.
Do I assume a specific PBH population to obtain the rate of mergers? We assume a log normal mass function in the numerical computations, but in general it doesn't. So it's possible to do the estimates for any distribution of primordial black holes. One thing that I didn't discuss. Okay. I didn't discuss the effect of an extended mass function, for example, in the suppression factors. But I'm not sure if the question. So
I think the first slide of your second part, where you talk about the PBH binary formation.
Mm-hmm.
Could you please go back to that slide?
Yes. Do you mean the simulation?
No, before that. I think it was the very first one. That one, yes. Yes, I think Ivanova is asking about this rate, if I understand correctly. I think the rates are completely independent on the
yes
population, right?
So this gives a rough estimate, rough numbers for the upper bounds for this, so that the largest numbers, at least for the early one, this is the large number, and for an upper bound. So I assume that f is 1, and the mass function is such that the mass function can be whatever actually. So and no suppression and so on. And for the late one, this is a more like a typical number. So it might be a bit larger, but this is something that I haven't studied in detail. So if you have lots of clustering, then the late formation can be larger.
Okay. Actually, I was confused by this slide because you're saying that the rate of the formation rate for random, like PBH moving randomly, is much higher than if PBH are already like in a halo, and higher by 5 orders of magnitude.
The early one corresponds to when the PBHs are at rest. So they are at rest, they decouple, and then they fall into each other. If in the late case they are in a halo, the halos are much less dense than the early universe because the universe expands. And also the binaries the PBHs are moving, so it's a bit more difficult to have close encounters. In the early universe, if you have a pair, so every nearby pair will interact and form a bound system. So that's why the early rate is much larger.
Okay.
Or this is at least what I expect. But of course, so the numbers in this slide did change when we discussed different suppression factors. For example, if you look at the rate, just to here, so this 10 to 5 corresponds to roughly the unsuppressed case. So the actual rate is if you account for the suppression in halos, then it's lower. So yeah.
Okay, thanks. So there's another question again by Ivanova, and asking if for this rate do you assume that PBHs are monochromatic?
Not necessarily. So in the simulation, we did a simulation for monochromatic and non-monochromatic cases, but the non-monochromatic just had 3 solar mass, 10 solar mass, and 30 solar mass black hole. So it's a toy model. But our analytic estimates, so for example, this merger rate has can be computed for arbitrary mass functions. When we compute suppression in clusters, then we assume a monochromatic distribution. And also this distribution of the merger rate of perturbed binaries, we assume a monochromatic distribution. But so the effect, if you have a non-monochromatic distribution, there is one thing that I need to say before is that the distribution is relatively narrow. What we observe, the LIGO cannot correspond to a very wide distribution. So the monochromatic assumption is not that bad. But anyway, if we compute this 3-body formation, then the main effect that has to be accounted for, that if you have a 3-body system of different mass binaries, then usually the lightest binary is ejected. So this population of binaries will likely contain the heavier tail of the mass distribution, because all the lighter ones are ejected, and also the lighter binaries are more easily disrupted.
Okay, thanks. There's another question by Marcos Ariel Ramirez. He's asking whether you're aware of a recent work by, I think, Celine Böhm, in which they use a curta metric for the PBH and found much more coalescence time. That means far less stringent bound for FPBH from LIGO.
Yes, I am aware. So the metric that they assume describes primordial black holes with growing mass, and such. So if you look at the behavior of matter around the black hole in the curta metric, then you see that there is a continuous flux of dust or whatever is surrounding the black holes into the black hole, and I don't think this is a realistic description of accretion. And then there is one more issue for me with this, is that if you have all black holes, all of dark matter is in black holes, and the black hole accretes, then it has to accrete primordial black holes. So the situation is not what they describe. There is no uniform flow of dust into the black hole. It's usually what happens if you have this, even if you have lighter black holes or particles that you can have a flow into the black hole, but then it's not completely spherical symmetric, and you have this violent relaxation is the wrong word, but most of the particles will not fall directly into the black hole. They will form a cloud around the black hole, and this also has been studied. So, and it's easy to eat a cloud that has some velocity dispersion, because if the particles have a large velocity, they will. It's difficult for the black holes to eat them. So it's briefly, I think they make a specific assumption for accretion, which I think is not realistic. But of course, this deserves to be studied further.
Okay, great, thanks. Maybe a last question. Well, we have been running for more than an hour, so thanks, Hardi. Thank you very much for this nice talk.
Thank you.
And a couple of comments or announcements better. So next week we'll have another webinar, this time by Gino Isidori. And in 2 weeks time we'll have Kip Thorne. So we're super happy of this talk. So please keep tuned and get connected next week for Gino's talk. And thanks again, Hardi. Thank you very much.
Thank you.
See you guys next week.
Bye.
Ciao.